up to this point, we have made a model, and I have tried to be very upfront about the fact that you need to love your model. Um, but we should probably temper a little bit of enthusiasm for our model and think about what do we really want our model to accomplish. So, with the example that we were playing with the amount of SO2 in the atmosphere, we had three different predictors that we could potentially put into the model. We had average temperature, number of factories, and population. And so, based upon those predictors, what we wanted to do is we wanted to come up with a model that would predict the amount of SO2 in the atmosphere. That is our goal of the model. We also would like to be able to look at the model and interpret the parameters. You know, is it positive related to SO2 or is it negatively related to SO2? And those are all the basic, things that we want to get out of a statistical model. We want to actually interpret the model and make some predictions based upon the model, as opposed to just simply, getting our p-values and marching on. We would really like to understand something. So this is where this important concept comes into play, which is called model selection. And model selection, as the name implies, is the process of selecting the appropriate model. Because again, we have a bunch of predictors, but it could be that some of those predictors don't really mean anything for SO2, and we wouldn't want to include those in the model. And so model selection is always going to be a compromise between having a very complex model with lots and lots of different predictors and the ability for that model to actually have interpretable parameter estimates or hypothesis testing even. And so that the compromise is there because if we have what's called an over-parameterized model, which is just simply a model that has too many parameters in it, the consequence of having an over-parameterized model is that, remember, every time we estimate a parameter, we lose a degree of freedom. So we're going to lose a little bit of statistical power when it comes to the hypothesis testing part. But we've also lost a random variable, if we're keeping track of the degrees of freedom, every time we add a parameter, and as a consequence, the uncertainty around our parameter estimates will increase. And so what we would like to have is we would like to have as much certainty as possible around the parameters that actually matter for our purposes, right? For our modeling purposes. And so there's a number of different ways in which people do model selection. This is probably one of the more, I guess you could say, subjective parts of statistical analysis. If we go back and look at the model that we were playing with, here I've made a model where I'm simply trying to predict SO2 as a function of average temperature, number of factories, and population. And, I can go ahead and there's my parameter estimates right here for the slope for temperature and factories as well as population. And what I would like to do is I'd like to figure out what really should go in that model. Because again, right now we're estimating three different slopes. Every time we estimate a slope, we're going to have more uncertainty around all of our slopes. And so how do we do that? There's a number of different ways. The first thing I want to draw your attention to as to another part of why it's important that we come up with, I guess, what we could refer to as the most parsimonious model. That's probably the best way to think about it, is to go back and think about how one of the metrics that we use of how well our model is performing is to look at the amount of variation that is explained. And we've already talked about that when we calculated the R squared, right? And just to remind ourselves, I'm going to make myself big again. Oh yeah, it's going to be one of those days. So if we oh, that was great. If we remind ourselves on the old whiteboard with the light up there, but the R squared was simply the sums of squares associated with our model divided by the total sums of squares, right? So our model sums of squares, our total sums of squares, that's what gave us our R squared. And that's a great measure of how well our model is doing at describing our sample, our data on hand. Now, there is another R squared that we have just kind of conveniently been ignoring, which is what's known as the adjusted R squared. And so the adjusted R squared is calculated slightly differently. I'll make myself big again so we can use this awesome whiteboard that I have. Awesome whiteboard. So the R squared adjusted, that's me writing R squared adjusted, is going to equal 1 minus the mean squared of the error divided by the mean squared total, okay? And let's remind ourselves that the total mean squared is the exact same thing as the variance. Remember when we were putting together ANOVA tables, we didn't even bother calculating the total mean squared because it's not used in the actual analysis of variance, but it is used when we're calculating what's called the adjusted R squared. So there's a number of different ways that we can kind of think about what the adjusted R squared is telling us. The first way that we can interpret this adjusted R squared is the adjusted R squared tells us something about how well our model is describing the variation in the population overall, as opposed to the R squared, which is telling us something about how much of the variation in our sample our model is explaining. And so that's one way that you can kind of keep track in your head of how those two things are different. The R squared adjusted, I'm going to move out of the way, the R squared adjusted you can think of as being, we have this model. Now, how well would this model perform on another sample in that population? Like overall, the overall population parameters are being described by the adjusted R squared, whereas the normal R squared, which is the one that usually people report, the normal R squared is all about how good our model is doing at explaining the variation within our sample. Okay, so now at least we know what that adjusted R squared is all about. Usually for the types of linear models that we'll be playing with in this class and that most of us will play with in the future, the R squared is the appropriate one to communicate to people, just because you are building the model based upon your sample and you are making inferences based upon your sample, and you're not really going back out to that population and multiply sampling and getting an idea of what the overall population parameter might look like. But the R squared is not, it's totally fine to communicate the adjusted R squared instead of the R squared. Some people like to do it because they think of it as being a little bit more conservative, because the adjusted R squared will tend to be less than the normal R squared. But another thing that the adjusted R squared is important for is this idea of model selection. And actually using the adjusted R squared is probably the oldest method out there for doing model selection. The older method would just be eyeballing it and being happy with it. The adjusted R squared was an attempt to be a little bit less subjective when it comes to model selection. And so let's look at how the adjusted R squared behaves, and then you'll see why it might be a useful tool for model selection. And spoiler alert, we're not going to use the adjusted R squared for model selection. There are better options out there in the world right now. But I want to point out how these things are different and how they behave differently with one another. So right now, based upon our sample, we have an R squared of almost 40% of the variation is being explained. And then we have our adjusted R squared saying, we're really only explaining 35% of the variation. And so now let's dump more stuff in the model, because this is a phenomenon about the normal R squared that's actually really important to keep track of. So what I'm going to do is I'm going to create some junk data, which I am going to cleverly call junk 1, junk 2, junk 3, junk 4. Okay, so, and this is going to be junk in that these are just going to be random variables drawn from a normal distribution. There is nothing about them that we think in any way, shape, or form should predict the amount of SO2. This is just garbage that we're just throwing in the model because we're bored. If you do such a thing when you're bored. And so here's now our model. You can see we have 1, 2, 3, 4, 5, 6, 7 predictors. And I'm going to call it mod dumb because it's a pretty dumb model. We just put 3 hunks of junk in there. So I'm going to go ahead and I'm going to first create those objects. Okay. And now I will go ahead and I will say, what is the summary of mod.dum? All right, what do we got here? Well, now we're explaining 41%, almost 42% of the variation. And if we compare that back with our original model, which only had 3 predictors in it, we were explaining 39.9% of the variations. So it seems as though the fact that we threw junk into the model, we're explaining more and more of the variation. In fact, you could just keep adding things into the model and your R squared is always going to go up. But let's take a look at the adjusted R squared. And so here's our adjusted R squared with the model that only had temperature, factories, or population in there. And then here is the adjusted R squared when we put junk in there. So notice that the adjusted R squared is going down when we start to add parameters or we start estimating parameters that are not important for predicting SO2, whereas the normal R squared continues to go up. So that's another reason why model selection is important, because, you know, again, we could throw 10 other junk predictors in there that are just normal random variables, and our R squared is going to keep going up, whereas our adjusted R squared will not. It'll plateau and then it will start to decrease. So one of the oldest methods, again, of doing model selection was to explore various models and keep an eye on the adjusted R squared to decide whether or not you want to include or exclude something from the model. Okay, so I wanted to go over that because I know that adjusted R squared is there, and it's kind of always nice to know what all of the output from these things mean, and just to understand what the adjusted R squared is actually doing. It is a more conservative estimate of the amount of variation that you can actually explain based upon your model, and it certainly penalizes you when you start to over-parameterize the model. And again, we don't want to over-parameterize the model because we're really keen on having a model where we have good, solid parameter estimates, and we would like the uncertainty around those parameter estimates to be as good as possible. Okay, so now let's talk about the 21st century and what people are thinking about as far as model selection. Model selection in the current days. The strategy that most people use now for doing model selection is going to be based on what's known as information theory, or specifically information criterion. And let me erase that and then I'll rewrite it. Looking at the fancy board here, one of the most commonly used forms of information criterion that people use is what's called AIC information criterion, or AIC for short. I'm sure most of you have at one point seen AIC in a paper. And what is AIC? AIC is going to give us a score that we're going to use to determine what model among the models that we're comparing is the best model. And what it's going to be is it's going to be 2 times the number of parameters in our model, which is usually shown as K, minus 2 times the log likelihood of the model. And again, we've already played around a little bit with log likelihoods when we calculated the probability of getting a particular value drawn from a particular, type of a distribution. And here we're doing the same thing, except here we can extract the log likelihood for our entire linear model. Okay, it's a parametric modeling scheme. We actually are using the normal probability density function behind the hood, which means that we are able to calculate what's known as the log likelihood of our model. In a general sense, what we are interested in finding is, among the models that we're interested in comparing, the model that has the lowest AIC value is generally considered to be the best model of the models that you're comparing. There's no way that it would know. There could be a much better model out there, but you just failed to explore that model because maybe you didn't have the correct covariates or whatever it might be. But what we'd like to find is the model that has the lowest AIC score. And a general rule of thumb, and it really is just kind of a very general kind of rule of thumb, is that AIC scores that are within two AIC units of one another are considered to be in the same family of models. So if you have the best model and it has a particular AIC value, but then you have another model that has an AIC score that's within two of the best one, both of those models might be considered to be in the family of best models. And so you can have multiple models that are in the family of best models, and then what you would do is decide what model you want to go with. And again, it's your model. You can do whatever you want with your model. So again, what do we have? We have our penalty term here. We're penalizing 2 times the number of parameters. So every time we add a parameter, that value is going to increase, and then we're going to subtract that from the -2 times the log likelihood of our model, and that's going to give us our AIC scores. There are different flavors of AIC. This is kind of the standard AIC one, but there are ones that are referred to as being corrected, AIC corrected. And by corrected, what they're referring to is if you have a small sample size. And so it's just an extra penalty that you get by having small sample sizes. And I included the maths for the corrected AIC scores in the handout. We're not going to worry about it too much. Just be aware of what that AICC is. Some people like to use that because it's more conservative, and that's fine. For me, I just kind of like to explore, look at the AICs, and I don't worry terribly that much about the importance of a delta AIC of 2. Yeah, so that's AIC. The second one that we might want to think about is what's called BIC. And BIC, the B stands for Bayesian, so it's Bayesian Information Criterion. As we'll see in a couple of seconds, there's nothing Bayesian about this. In fact, we can go ahead and write up right now what our penalty is going to be. So the difference between AIC and BIC, AIC just does 2 times the number of parameters. What BIC does is it does the log of our sample times the number of parameters, and then minus that 2 times the log likelihood. And that minus 2 times the log likelihood, sometimes you'll see that being referred to as the deviance. But here's our penalty term. So with AIC, it's just 2 times the number of parameters, and with BIC, it's our sample size times the number of parameters. And that will give us the BIC score, and then the same rules will apply with the BIC score, which is that you want to find the one with the lowest value. The one with the lowest value should be the most parsimonious model, where you're extracting the most amount of information with the fewest number of parameters. Now, in older papers, and if anybody is really into tinkering with really old computers, BIC used to be called Schwartz criterion. There's actually nothing Bayesian about this. This approach was justified in a Bayesian framework in the original paper, but the function itself, there's nothing, we've played with Bayes' theorem. There's nothing directly Bayesian about this at all. And what happened was, I guess it was probably in the late 90s, maybe early 2000s, people shifted to start calling it BIC, Bayesian Information Criterion. Again, it used to be called the Schwartz criterion. I think what happened was people decided that Schwartz criterion didn't sound as fancy as Bayesian Information Criterion, and so they started calling it BIC. I don't know if that's the true history of why they switched over to BIC, but my internal cynic thinks that that's probably the reason, is it just sounds cooler. So here's our 2 different types of information criterion that we can play with. And let's just go ahead and we'll play with that a little bit in R and see what it looks like, and we can start to kind of compare some different models. So I'm going to scoop myself down into the corner there. I'm going to go ahead and I'm going to start with just our model, not the one including the junk that we played with before, but this is just one where we have average temperature, number of factories, and population. there's our model. We got our model. There's the parameter estimates of our model. We could do summary of our model, of course, summary, right? And there's our R squared, and we already talked about what the adjusted R squared is. And so first, as I pointed out, we can always extract the log likelihood or the likelihood of any linear model. And so we could actually extract that using a function called log like. And then I'm just going to give it the name of our model object. And that is the log likelihood of the model, okay? Again, likelihoods really only mean something relative to other likelihoods, right? But we are able to extract that log likelihood of our model. And so we could, by longhand if we wanted to, we could calculate what the AIC is. So it's going to be 2 times the number of parameters. So here we have 1, 2, 3 slopes. Hidden in there is going to be an intercept. And then for this particular function here, it's also including the error as being a parameter. So, okay, let's go along with that. So I'm going to say 2 times 5. And then I'm going to subtract from that 2 times the log likelihood of our model. All right. And so that is our AIC score for that particular model. Now, by itself, it doesn't mean anything. AIC scores will only mean something in regards to other models analyzing the same data. So if you have your own data set at home and you're playing with it and you're like, well, my AIC was -2, and that's way lower than 75. I must have a better model than Jim. You very well could have a better model than me, but AIC is not telling you that. AIC is only relevant if you're comparing models using the exact same data, which means that you also can't use AIC to ask what transformation is better. That would not be acceptable. The data cannot change. The only thing that can change are the parameters that you're using to describe your data. And so let's go ahead and use capital AIC as a function, and we can go ahead and put our model in there. And there we have it. Okay, so we have a built-in function called AIC, which will give us the AIC of the model. We know how it was calculated because we did it right up there. Okay. Within that AIC function, question mark AIC, okay, you'll see that k equals 2 is the default. And again, k is the penalty per parameter. And that is what we drew up here on the board with this 2k right there. Okay. So if we wanted to do BIC, we could actually use that AIC function. We're going to give it our model. And then I'm going to say k equals the log of 41. And I'm picking 41 because that's how big our sample is. That's how many observations we have, right? So here's our SO2. If I were to ask for the length of SO2, it's 41. So I take the log of that and I calculate the AIC. And now that is my BIC. Okay? Again, this is in units of BIC. This is in units of AIC. It's the same model. They're just going to be different values. A shortcut, which is a relatively new shortcut in the R universe, is there's actually a built-in function called BIC. Model. That's all I need to give it. And there we go. So it'll calculate it for us. We don't have to do it. We don't have to do it by hand. All right. So let's think about comparing them. We have these 3 different predictors, and we'll do this longhand, and it's totally valid to do it longhand, where I am going to create a bunch of models, all the possible models, which means that I'm going to put here, there are 7 possible models. So there are these models here, where I only include average temperature, I only include number of factories, I only include population. And then I have these 3 models here where I'm including 2 possible predictors, average temperature and number of factories, average temperature and population, number of factories and population. And then finally, I have this last model, which is the big fat model that includes all of those predictors. And so all I'm going to do is I'm going to run those models, and then I'm going to calculate the AIC after each model. I don't know if I've mentioned this in the past, but this little semicolon here, that's just a way that you can put multiple functions on the same line. So that's why that's there. So I'll go ahead and I'll do mod 1.1. So this is the model with just average temperature. And I get an AIC of 78.54. So now let's compare that against the model that only has number of factories. 87.38. Well, now just between those two models, average temperature is the much better model than number of factories. So we already kind of know that if we are not going to probably be sticking with a model that only includes number of factories. So let's do the same thing for population. Population also not so good, right? And so of those three models that we looked at, the best one is the one that includes average temperature. So now let's go a little bit further and let's explore some models with two predictors in there. And so I'll go ahead and I'll do that. So this is the one that has average temperature and number of factories. 76.6, that's actually better than the one with just average temperature. But if we look here, 70s, it's within 2 AIC units, which means that both of those models could be considered to be in the same family of best models. So let's see here, what one was that? That was average temperature and number of factories. Let's look at average temperature and population. Now our AIC is going back up, 79.66. That's quite a bit different from this one. It's actually in that same family of models as the one that only included average temperature. But right now, our best model seems to be average temperature and number of factories. And now let's explore a model where we have number of factories and population in there. And it's 81.89. So, that's not so great, right? And so, yeah, where are we at? Their best model that we have come up with thus far is this one. Right? It is the one that includes average temperature and number of factories. So now let's go and we can look at our 7th model. And that gives us 75.4428. So according to our AIC scores, our best model is the model that includes all 3 of those predictors. Our second best model is the one that only includes average temperature and number of factories. And now that we've gotten down to this 75.44, right? So if I were to take that plus 2. Yeah, the only one that is under 77.44 is this model. And so average temperature right up here, our first model that we looked at, isn't really within that family of best models. The best model that we can come up with appears to be model 3.1, which includes all 3 predictors. Okay, and so that can get pretty difficult to do by hand if you know, to type in all this stuff. Like we had 7 models that we needed to consider with only 3 predictors. If we had 6 predictors in there, we would have had 64 models that we would have had to go through. And so the strategy that people use is what's called a stepwise model selection approach. And just starting with backwards stepwise procedure, what you would do is you would start with this model, this big giant fat full model, and then you would say, does my AIC get any better if I start removing any of these? And if it does get better, then we'll go ahead and remove that, and then we'll do it again, and then we'll ask, does it get better? Does it get better? And so I can use a built-in function called step AIC. And then I'm going to go ahead and I'm going to give it my model. And let's remind ourselves, the model is the full model, but it's called model. So we'll call it that. So I will go ahead and I'll put model in there. And I'll run that. And what you can see is that it starts here, it's got an AIC, and it's deciding that the best thing it can possibly do is nothing. So it's not changing anything about the model. Now, those of you that are paying close attention, you'll notice that that AIC value, negative 42.91, that is a little different from this. And that's because step AIC is actually using a different internal function called extract AIC. And so again, if we stick with our big fat full model, there's the AIC for our big fat full model. If we were to type extract AIC model, we get a different answer. But that's okay, because the only difference between those two approaches is that the AIC function, remember it included the error term as being a parameter, so it had 5. And when you use the extract AIC function, it's saying that there's only 4. So it's just saying that there's the intercept and the 3 slopes that you've calculated. The reason why it doesn't matter is as long as you use the same function basically as long as you consistently calculate AIC in the same way, it doesn't really matter how you are counting parameters. So we can prove that to ourselves. Let's look at the AIC for mod 3.1, and then let's use the extract AIC function for mod 2.1, 3.1, mod, Jim, keep it together, 3.1, right? So these are our different values. Let's compare that against some other model. Let's say we compare it against mod 2.1. Okay. So the reason why it doesn't matter, I keep saying it doesn't matter. Let's look at the difference between the AIC scores for our best model using the AIC function and this other model, right? So we could say, well, what is the delta AIC? And that just means the difference in those AIC scores. It's 1.19, which again, it's within that delta AIC of 2 window, so both of those models would be considered in the family of best models. We could similarly use the values from the extract AIC function, where I can say it's going to be that minus that, and we get the exact same answer. So the difference between those AIC scores is the same, even though it's calculated slightly differently. And it's only calculated slightly differently in that the AIC function gives you, it includes the error as a parameter, so we had 5 parameters, whereas the extract AIC function doesn't include the error in there. It only includes the intercept and then the 3 slopes. And that's why those values are different. But again, it doesn't matter as long as you are careful to always use the same method for calculating your AIC values, which usually shouldn't be that big of a problem because, doing model selection, that's private time. You can do whatever you want, and then you just come up with the model. So it's not like, those numbers, again, mean nothing outside of the context of these data and this model. And so just be aware of that, because different programs will count the number of parameters slightly differently. And if you're going to be comparing models using AIC, which you will, just make sure that you're using the same function every time that you do it. Okay, and so let's. I'm gonna make another dumb model, and I'm gonna do that because I'm gonna throw in all of that junk that we had. Remember this model, mod dumb junk. And I'm gonna rerun that model, and I'm gonna do step on that, so that way we can see each step. Because basically we didn't do anything to the model. We gave this model up here to the step function, and it decided that the best thing it could do was nothing. And so let's put this dumb model in there to see whether or not it starts behaving a little bit more like we might expect model selection to behave. So let's go all the way up to the top. These are all of our steps. So the first step, we have this AIC value here of negative 36.3. And R is going through here and saying, if we were to drop junk 2, we're going to go all the way down to negative 38.274. And so at this first step, it's going to drop junk 2. And now you'll see at this step here, junk 2 is no longer considered part of the model. And then here is the AIC going into that first one, which is this AIC score right here. So now we're at the second step. And now R is saying, you know what? If I remove junk 3, our AIC gets even lower. And so, you know, the computer's pretty happy with that. And so it goes ahead, it drops that. And so now we have a simpler model with only junk 1 and junk 4. Next step, dropping junk 4 will take us down to negative 42.160 from negative 40.23. So it's a better model. Lower the AIC, the better the model. And so it's going to drop junk 4. Now we're down to here, and it's deciding, you know what? We could also drop junk 1. It would increase it'll decrease the AIC value, which will increase how happy we are with our model. And it'll go ahead and it'll drop that. And then here we are. And now it's saying that the best thing it can do is nothing. And so at the end, what the step function will do is right there, it is telling you what your best model is. And so you could just take that and you could cut and paste that, you know, final mod will get, and then you can just go ahead and paste that in there, and there we have it. We have our final model, okay? One thing that the step function won't do is it won't tell you whether or not you have multiple models that are in the family of best models. And so that's something you're gonna have to do on your own. So for example, here where we remove nothing, this is our AIC score, but that is clearly within 2 of that. And so maybe you want to keep junk 1 in there, maybe you don't. And again, that is entirely up to you because it's your model and there is no, you know, concrete way of doing model selection. All model selection at the end of the day is a little bit subjective. Okay, so that is what's referred to as backwards stepwise. And so let me put that back down there, and I can even be more, copy, paste, more explicit to say that the direction is backwards. And it's called backwards because it's starting from the fullest possible model, and then it's starting to remove things, okay? The second approach, I should also mention that within this step function here, if we wanted to use BIC instead of AIC, we would say that K equals the log of our sample, which is 41. And now it's using BIC. And remember I mentioned that BIC tends to be a little bit more conservative with smaller samples. Notice here, I'm pointing like you can tell where I'm pointing to. Notice here that the best model using BIC is one that only includes average temperature and number of factories. Population has been removed. And so that's just a nice illustration of the fact that indeed BIC is a little bit more conservative than AIC. Okay, so the other way besides doing backwards is we could do what's called forward. And a lot of times people, and there's philosophically, it doesn't really matter what you do, just pick one and be happy with it. Like 30 years ago, there were a bunch of arguments in the literature about which is best. And like in my personal experience, I always pretty much arrive at the exact same model. And again, I own the fact that it's my model, so maybe I want to include stuff in there that AIC says I shouldn't. And I can do whatever I want. Yeah, I'm a big boy now. Okay, so the other way is forward stepwise selection. And forward stepwise selection is the opposite of backwards, where you're going to start with the simplest model possible. And if we think about it, what is the simplest model possible? It would be a model where we only estimate the intercept. Okay, so that would be the simplest possible model. So I can even write in here simplest mod. And it'll be a linear model where we're going to try to predict SO2 as being some function of nothing. So all that's going to do, that's an intercept only model. 3.153, that I bet is the mean of SO2. It better be. Whew, thank goodness. Okay, so that's our simplest model. And then what we need to tell the step function if we're going to do forward is we have to give it the scope of models that it is possibly going to explore. Meaning that we need to have the lower scope. The lower scope is that right there, that super simple model where all we're doing is an intercept. The upper limit of that model is going to be our super big full model. And let's just keep playing with mod dumb because we have it. And so I'm going to go ahead, I'm going to get rid of that. So we have mod dumb. We have our simplest mod. And so let's go ahead and we'll use the step function. And then we will take the simplest, why am I having trouble? Simplest. Take our simplest model, because that's going to be the starting point. That's where it's going to start from. And you don't necessarily have to start it with just the intercept. Like maybe you know going in that you really want number of factories to be in there. And then for the simplest model, number of factories. And that's totally fine. Absolutely fine. But I'm going to start here with super simple one, which is just the intercept. And then the next thing I have to do is I have to tell it the scope. And the scope is going to be a little list. And then I have to give it its upper and its lower bounds. So the upper bound is going to equal our mod dumb. Okay? And then our lower bound is going to be squiggly 1, which again is just saying our lowest bound is just give me the intercept. That's all I can do. And then we're going to have to tell it what direction it's in. Direction equals forward. So I go ahead and I do that. And again, here we're starting with just an intercept. There's our AIC value. If we were to add average temperature into that, we're going to go down quite a bit. We're going to go from negative 27 all the way down to negative 39. So we go ahead and we add average temperature to the model. And we learn that if we were to add the number of factories, it would go down even more. So we go ahead and we add the number of factories. And now we say, well, if we were to add population, it would go down even more, right? It would go from negative 41.71 to negative 42.91. And so we add that into the model. And then we stop. That's the best that we can do. That's the lowest AIC score that we can really come up with based upon these predictors. And so again, here's our final model. And usually forward and backwards will give very similar answers. They will usually only differ by one predictor that's in the model. So it's really not that huge of a deal. And I usually use backwards just because I'm a little lazy. And with that, all I have to do is just put my full model into that step function and it does it all for me. So out of my own personal laziness, I kind of like doing backwards selection. Right. Yeah, so that's model selection. The last thing that I want to kind of think about as just a caveat to make sure that we feel comfortable with what AIC is doing is I just want to go back to thinking about the likelihood of our data given parameter estimates. And so I'm going to start with those values, 2, 5, 8, and 7. And recall that we can use the probability density function for a normal to calculate what the likelihood is, right? What the log likelihood is. So I could say dnorm, and I'm going to give it my vals. And then I'm going to test it. I'm going to pretend that, let's say that this distribution that I'm going to calculate an AIC score for, let's say that it has a mean equal to 2 and a standard deviation equal to 1. And then I'm going to say log equals true. So that way I can just simply take the sum instead of the product of all of those probabilities. Again, so that way the computer is happy and not getting rounding problems. So I'm going to go ahead and I'm going to take the sum of that. That right there, that's the log likelihood. Okay, we have calculated the log likelihood of those data given a mean of 2 and a standard deviation of 1. And we could test, different models. We could go ahead and let's say that it's 5.5. Okay, well that has a much higher likelihood than that has, right? And we haven't changed at all the number of parameters. We just have our log likelihoods in there. So I'm going to go ahead and I'm going to compare 3 different hypotheses. Okay. Hypothesis 1 is that these data were drawn from a normal distribution with a mean of 1 and a standard or a mean of 2 and a standard deviation of 1. Hypothesis 2 is that those values are drawn from a normal distribution with a mean of 5.5 and a standard deviation of 1. And then the third hypothesis will be a mean of 5.5, and then I'll actually use the maximum likelihood estimate for the standard deviation of those values. So you can already kind of imagine that this model is probably going to be a pretty good model because I'm actually using the maximum likelihood estimates. And I think that's where I got that 5.5 from. Mean of vals is 5.5, right? And so going into this, we expect this to be the best model because it's the probability of our data given the parameters, and the parameters that we're actually putting in that model are the maximum likelihood estimates. They can't get any better. But for fun, let's go ahead and we will compare those 3 hypotheses. And so let's just do that with using the AIC scores. And so 2 times the number of parameters, we've estimated 2 parameters, right? We've estimated a parameter for the mean, and we have an estimate for the standard deviation. And then we're going to multiply that, or we're going to subtract 2 times the log likelihood of our hypothesis. All right. That is our AIC score for this model, the first model. We can do the exact same thing and calculate our AIC score for the second model. Much better. And we could calculate it for our third model. Also much better. So based upon these 3 models, and they're 3 models simply because we had different parameter estimates, we can go ahead and we can use those AIC scores and say, this one appears to be the best. We can also do something similar. I'm going to create some newer and improved data. Let's see here. All right, so there's 2 different options here, right? So I have values for one, values for a sample from a second one, and then I've combined them all together. And what we can do in this kind of situation is we can ask, should these data be modeled as being drawn from 2 distributions, or am I okay modeling them from 1 distribution? Meaning 1 mean and 1 standard deviation. And so let's go ahead and we can compare those 2. So let's look at the log likelihood. I'm going to create some objects here. This is the log likelihood for just values 1, right? So just for those values. And again, I'm going to calculate it by looking at the dnorm function. I'm going to give it those values, and I'm going to go ahead and I'm going to use the maximum likelihood estimate. Okay, so this is the best I can do for values 1 is right there. And I can go ahead and I can do the exact same thing for values 2. Okay, so I got now the log likelihood that these guys are drawn from a normal distribution with a mean of 5.5 and a standard deviation of 2.645751. And likewise, okay, so that's the log likelihood, and then I could do the log likelihood for the second batch where I'm basically using the maximum likelihood estimate for the mean and the standard deviation for those. So here, keeping track of what we're doing, we have 4 parameters, right? The other the other type of model that we might want to compare that against is what we can call the reduced model. And so the reduced model is going to be a model where we combine all of these together into one. So I'm going to call that log like reduced. And it's reduced because it has fewer parameters. That's the only reason why it's reduced. That's why we call it reduced. So I'm going to go ahead and I'm going to do that. So now I'm using the combined data together, and I'm still going to use the maximum likelihood estimate for the mean for the data combined and the standard deviation of all those data combined. And I'm going to calculate that log likelihood. And so now to compare those two, what I need is I need the log likelihood for the full model. So that's the log likelihood for 2 parameters for values 1. This is the log likelihood for 2 parameters, volume 2. To come up with the overall log likelihood of that model, I can call the object log like full. And then all I have to do is add this plus that. Okay, just add those 2 log likelihoods together. Again, we like using log likelihoods because it's easy to add things more than it would be to kind of multiply all those probabilities together. But now we have a log likelihood for the full model. And we have a log likelihood for the reduced model. So now what we want to do is we want to use AIC to choose which of those 2 might be the best way to model these data. And so we do that. Let's start with our full model, right? This is where we calculated the total of 4 parameters, 2 means and 2 standard deviations. So we take that. We are going to say 2 times the number of parameters minus 2 times the log likelihood. That gives us our AIC score for that bigger model. And now let's compare that against the simpler model. And the simpler model is going to be 2 times the number of parameters. In this case, we have 2 parameters because we only estimated 1 mean and 1 standard deviation, minus 2 times, and then it was the log likelihood of the reduced model. And you can see that it has a higher AIC score. So now based upon this, the better model is the one where we model these 2 different samples as being modeled from 2 different distributions as opposed to being modeled as a simple as one distribution. But it gets even better than that. We can actually do hypothesis testing if we wanted to. Since we're talking about log likelihoods, okay, we've talked about AIC, we know that we can use AIC approaches. We might decide that we really want to do hypothesis testing. And so because these models are what are referred to as being nested models, they are nested because the full model and the reduced model is nested within the full model. The data has not changed. You're just lumping things together, so they're nested within one another. We can use something that's called a log likelihood ratio test. And the log likelihood ratio test is simply you're looking at the ratio of these 2 log likelihoods. Okay, and so I can draw on the board here real quick. Say goodbye to AIC. I know it was fun, but we gotta go. All right, I'm gonna make myself bigger so we can think about how to calculate a likelihood ratio test. That is something that does pop up a lot. So the likelihood ratio test is simply gonna be -2 times the log of what? Of the likelihood of the reduced model. So the likelihood of the reduced divided by the likelihood of the full. Okay, that's the ratio that we're looking at here. This is when we're calculating our likelihood ratio test statistic. Again, we like logs because logs are easier to deal with. And so we could also write this as -2 times, and since we're going to be in log land, we could say it's going to be -2 times the difference between the log likelihood, having troubles, log likelihood of the reduced minus the log likelihood of the full, because the arithmetic is just simply easier to do it that way. And that is going to give us the same thing, where we're going to calculate a likelihood ratio test statistic. All right, so I'm going to say we got our likelihood ratio test, and I know that one of these is spelled wrong because I screwed up. Let's fix that. Okay, and so here I am doing it. So, well, really, log like fool. Oh yeah. There we have it. So that is our likelihood ratio right there. And then we could go ahead and we could compare that against chi-square distribution, p chi-squa, where I'm going to give it the LRT. Here we are dealing with a model that had 4 parameters versus one that had 2 parameters. So our degrees of freedom will be 2. That is the number of free parameters that differs between those 2 models. And then, of course, I'll say lower tail equals false. And there's the p-value. So those models are significantly different from one another, meaning that our full model, the one that had 4 parameters in it, is significantly better than the one that only had 2 in it. So that's likelihood ratio test, and that's a different way that we can do hypothesis testing with this. And for fun, I like to use that word fun, right? We can, let's go back to our original data one last time, and let's compare the model where all we do is estimate the intercept, so our reduced model, and let's compare that against our full model, the one where we have all 3 of these. And we could similarly do the exact same thing using a likelihood ratio test. Log like mod reduced is that. And then we will have the log like mod 3.1 is that, okay? And so now we can just pop those into the arithmetic for the likelihood ratio test, which is right there, right? Notice how here it's 2 degrees of freedom. That is based upon, yeah, so this is the log likelihood of our reduced model. So we have an intercept and an error. This is the log likelihood of the full model, which is the intercept, the 3 slopes, and again, it's including the error term in there. And so we could compare that to LRT, compare that against chi-square distribution, p chi-squa, LRT. It differs in 3 degrees of freedom. And lower dot tail equals false. False spelled correctly helps. Okay, and so significantly different. And there's actually a library LM test, where you can do a likelihood ratio test and compare our 2 mods, mod reduced and mod dot 3.1, mod dot 3.1, and here we have it. Let's rerun both of those really quick. Not that one. Nope. Yeah, that one and that one. And so here's when we did it by hand. There's the p-value. Here's when we did it using the LR test function in R, which is the likelihood ratio test. Okay. I'm mentioning this because it's a different way that you can do hypothesis testing with linear models. And when we start doing generalized linear models, we're going to have to use likelihood ratio tests because we're not going to be able to use a classic ANOVA approach. So yeah, so that's it. Woo, that was a lot of stuff. But model selection, super important. Play around with it. It's not, once you kind of get past the part where you feel kind of like, I kind of wish something would just give me the right answer, it's not so bad. Model selection is not so bad. It's a fun part of building a model because remember, at the end of the day, you gotta love your model. All right.